All right, let's look at this example here. So there's this snack food called Bits and Bites, and there's 4 different kinds of them. You have your Shreddy, you have your Cheerio, you have your pretzel, and you have your cheesy bit. Now, I wrote them down in this order for a specific reason, is this is my order of preference. I like the Shreddies the best, then the Cheerios, then the pretzels, and then the cheesy bits are my least favorite. Everybody else has a different preference. Maybe somebody else's preference is, I'll do it in red, maybe somebody is Cheerio, cheesy bit, pretzel, Shreddy. That could be somebody else's. Or maybe somebody else likes the cheesy bits the best, and then the Shreddies, and then the Cheerios, and doesn't like the pretzels very much. So you can see there's lots and lots of different preferences. So here's my question, is how many people need to be in a room to guarantee two people share the same bits and bytes preference. So, well, if we think about it, imagine instead of bits and bytes preference, imagine it was your favorite number from 1 to 10. So you could ask, well, how many people need to be in a room to have 2 people to be guaranteed to share a preference? You don't know which 2 people, but it's guaranteed that 2 of the people will share a preference at least. Well, if we think about it, there's only 10 numbers, right? So in kind of the worst case scenario, if there's 10 people in a room, then each one of those 10 people could have a different favorite number. It's unlikely, but it's possible. But as soon as that 11th person enters the room, well, there's only 10 numbers. So that 11th person has to share a favorite number with somebody else. So that's kind of the idea with this. And that this whole process is an example of something called the pigeonhole principle, which we will get to a little bit later on in the course. But, so what do we need to do, our solution? Well, we need to figure out the number of preferences. And then just add 1 to it, because that extra person coming in makes there be more people than unique preferences, so that extra person must double up with somebody. Okay, so let's determine the number of preferences. Well, let's think of it like this. Same way with our choices. We have 4 choices. We have our first favorite choice, then our second, our third, and our least favorite, our 4th favorite of the bit and byte. Well, I have 4 different choices for what could be my favorite bit and byte. So I could choose any of them. So there's 4 choices for that. And let's say for me, of course, it is the Shreddy. Okay, that's chosen. So I can't choose it again. So the set of things that I can choose, rather than being, so for the first one, it is, for me anyway, I can choose any of them. In fact, anybody can choose any of them to be their favorite. But once they choose their favorite, well, you can't choose it as your second favorite either. It has to be something new. So I'm left with just the Cheerio, the pretzel, and the cheesy bit. And of course, I choose the pretzel. So there's only 3 choices for my second favorite. Similarly, well, my third favorite, which for me is the pretzel, there's 2 choices for that. I could choose between the pretzel and the cheesy bit. And finally, well, the only thing that's left for me to choose is the cheesy bit. That's my least favorite, so there's only one choice for that. So how many choices overall do I have? Well, I have 4 choices for my first guy, and 3 choices for my second guy, and 2 choices for my third guy, and 1 choice for my last guy. So this is going to be 4 times 3 times 2 times 1, which is, of course, 24. But look at this. I can write this as well as 4 factorial. You can see where these factorials are going to come into our lives here. So that's pretty cool. So there's 24 different preferences of bits and bytes. So that tells me that if 25 people are at a party, it is the minimum number. To guarantee two people share a preference. 24 preferences, so you could imagine 24 people all having different preferences, but that 25th person must double up with somebody. So that's how this style of counting works. All right, let's look at a different problem now. So, I think this is 44.4. Determine the number of unique words. And by words here, what I mean is any arrangement of letters. It doesn't need to be an English word. Any arrangement of letters I'm going to call a word. So determine the number of unique words you can make by arranging the letters S, C, P, and B. And by arranging, I mean once I use a letter, I can't use it again. So this should look quite familiar to you because we just did this problem. I picked the letters S, C, P, and B for a reason. S are Shreddies, C are Cheerios, P are pretzels, B are cheesy bits. So this is just, well, 4 choices for your first letter, 3 choices for your second letter, 2 choices for your first letter, 1 choice for your last letter, which is 4 factorial, which is 24 different arrangements of these letters to make unique words. Let's do one more. Again, that's quite easy, and then we'll up the difficulty. Determine the number of unique words you can make by arranging the letters A, B, C, D, E, F, G. Well, this is a pretty similar problem, but instead of having 4 letters, we have 7 letters. A, B, C, D, E, F, and G. That looks a little sloppy. Let me rewrite that. A, B, C, D, E, F, G. Okay. So again, I have 7 choices for my first letter. Let's say I choose E. Well, I chose E. I can't use it again. So there's 6 letters for the next letter, for the second letter. I could choose, let's say I chose B. And I keep going like that. So 5 choices, then 4 choices, then 3 choices, then 2 choices, then 1 choice. Well, that's just 7 factorial, which is 5,040. So again, nothing completely new or surprising. Here we just change the number of letters that we had. But we can make it a little more complicated. Well, if we notice here, all of the letters here are unique. They're all different. But what about situations where they aren't all different? Let's do the next example. I guess this was example 44.5. Let's do example 44.6. Let's determine, same idea, determine the number of unique words you can make by arranging the letters. Let's do these. C, A, N, A, D, A. So now it's a little bit different. So now we have 3 letters that are the same, 3 A's. So we're going to have to think about how to deal with that. Let me scroll up here. Okay. So probably the best way to think about it is as follows. Well, let's pretend all the letters are different. So I'm going to make this this is going to be an A1, an A2, and an A3. I'll make them different for now, but I don't want them to be different at the end. But for now, I'll just make them different, and we'll deal with the fallout afterwards. So how many ways are there of arranging these 6 potentially different letters, or ostensibly different letters? Well, that's easy. That is 6 factorial ways of arranging these letters if they were all different. Okay, no problem. But let me write down one of these arrangements. I'm just going to pick a weird one. I'm going to pick something along the lines of N, A1, A2, let's do D, C, A3. So there's an example of one of the arrangements of those 6 letters. But here's another one. So if all 6 letters are different, then I want to count this arrangement as different. And I also want to count this one as different. N, A, D, C, A. Maybe it'll be 1, 3, 2, for example. So if we think about it, what's going on here is, well, we need to count how many ways we can arrange the A's, the repeated letter, inside of each word, and that's how many kind of repeat words we have. So we need to count how many arrangements there are of the A's, and that's how many extra copies of each word we have. Okay, so let's do that. How many different ways can I arrange the A's inside of this word? Well, there are 3 different A's, so the number of arrangements of A's is, well, there's 3 choices for my first A. It's either A1, A2, or A3. Then once I choose that, there's 2 choices for my second A, and then 1 choice for my third. So that is, of course, 3 factorial. So let me scroll up here. Well, what does that mean? So for each of the 6 factorial words, we have 6 copies of the same word, because 3 factorial is 6. So each word, just like NAADCA, if we treat all the letters as different, then there are 6 copies of NAADCA in that count, because there's 6 different ways we can arrange the A's inside of that word. So in order to take that into account, we need to divide by the number of ways to arrange our A's, which is 3 factorial. So this is, let's write it down, 6 times 5 times 4 over 3 factorial, times 3 factorial here. So 6 times 5 times 4 times 3 factorial over 3 factorial. These guys cancel. So if we multiply this out, we get 120. So there are 120 different arrangements of the letters in Canada. So 120 different arrangements of the letters C-A, N-A, D-A, which is great. Let's do one more. So what about, I won't do the same setup, so this is example, I believe it's 44.6. So what about, let's do the letters W-I-N-N-I-P-E-G. So here, let's write down what we have. So we have 8 letters in total. Well, out of those 8 letters, we have 1 W, we have 2 I's, we have 2 N's, we have 1 P, we have 1 E, and we have 1 G. Let's make sure that I have them all. 1 plus 2 is 5, plus 1 is 6, 7, 8. 8 letters. I covered all of my cases. So, the number of arrangements of the word Winnipeg, well, we do the same thing. We pretend all of our letters are different. So there's 8 factorial ways of arranging those. But we need to divide by the number of ways of arranging any repeat letters. So our repeat letters are I and N. And how many ways are there of arranging those? Well, there's 2 factorial ways of arranging my I's and 2 factorial ways of arranging my N's. So this is, I will just tell you, that is 10,000 and 40. You can check that if you like as a little exercise to make sure you know how to deal with factorials. But that's how to count the number of arrangements of letters when you have repeat letters. So this 2 factorial would be for your I's, and this 2 factorial would be for your N's. Now this idea is going to be really important to us because we can solve a lot of counting problems using this idea of translating it into an arrangement of letters.